morning, students. Today we are going to talk about the mechanical properties of materials. So, basically the contents will be that first I will tell you broadly about the material properties that we generally consider, for example, when we will be designing a product, and then we will go specifically into the domain of mechanical properties, where we will talk about the concept of stress and strain. We will describe how these constitutive relationships are built. Then we will talk about certain material or mechanical properties of the material, which are very relevant towards this direction. For example, the tensile strength, the ductility, brittleness, resilience, toughness, impact strength of material. These are the things that we generally need when we have to develop a product or an engineering system which has to sustain a degree of mechanical loading. So, first of all, let us look into broadly the material properties. In the last lecture, I have told you broadly about the domain of materials. Now, we are talking about the material properties that one has to consider. So, towards that direction, if you look at it, that there is a 7, we call it a 7 parameter based grading of a material. Okay. So, the first in this direction is, of course, you have to always keep in mind the economic and environmental effect, okay, because if the material is very expensive, then it is of no use for for a mass production system. Just for an example, that suppose you need a very high stiffness in a particular mechanical system. Now, diamond is having the highest stiffness. Okay. So, something like the diamond bond is something like 1200 gigapascal. But can I make a mechanical system out of diamond? No. So, that is what we have to keep in our mind. The diamond is of course an extreme example, but the price and availability is a very important aspect in terms of choosing a material. We will cover about these things in one of the talks. I will tell you that what is the current prices and availability of the materials in the Indian context. Okay. So, that is one important point, that whether the price is affordable for a particular engineering system. Now, once again, so say for example, you are making a screwdriver or you are making a nail cutter. So, the type of material that you can afford in comparison to, suppose you are making an automobile, will be definitely of inferior grade. That means, the material cost is more important for products like automobile or for products like aircraft, for example. So, you can afford there slightly higher grade of materials. So, that is why the price plays a very important role. Another very important role in the economic factor in today's context is the recyclability of a material, because we always say that there is a life of a product and there is afterlife of a product. So, when the product is of no use, okay, what are you going to do with it? The whole system, all the mechanical components. Yesterday we have seen that in the last class, that 150 years, even if you can retrieve a piece of steel, you can actually put it into the melting process and you can reuse the steel. The steel has an excellent recyclability from that point of view. Now, if you think of a plastic product, can it have that kind of a recyclability? Well, can you use it again and again once that product is used for one purpose? Can you melt it and reshape it and give it another life? That is the point. So, recyclability refers to that. Now, not all materials have a good degree of recyclability. Then the other point is sustainability. Now, there I can give you a very interesting example. For example, a couple of years or a few years before, there was a discussion that we should go for earthen pots for tea in terms of say railway uses and things like that, and the logic was given that it will be more sustainable. It will be because you are not using plastic, so it will be less, the recyclability point of view also it will be good, and sustainability issue is that because it is clay, so it will, it will not create any harm to the environment. But a study was made at Institute of Science, Bangalore, and people found out that actually the plastic cup is more sustainable in comparison to the earthen pot, because when you are making the earthen pot, you are actually taking clay, you are heating it up to a high temperature level, and hence the energy that you are applying is actually much more, and in today's context energy is very very important. So, the energy that you require and the pollution that it creates while making this earthen pot is actually much more in comparison to the environmental pollution that will be there for making a plastic cup from a plastic mold. So, you see sustainability is a very important topic which has to be thought of from all different considerations. Now, the other interesting thing here is also the carbon emission, because as you know that I would rather say the emission of carbon dioxide or say NOx gases and things like that, because there is a footprint today. You cannot really develop your energy or develop for that matter supply energy to a system by creating too much of greenhouse gases, etc. So, that is what one has to keep in mind while choosing a material, particularly for the transport type of applications. So, these being basically the economic and environmental aspects. Okay. Mechanical aspects I will come later, because anyway we will be talking about the mechanical aspects. Now, there are some thermal aspects also that we generally consider. So, if you look at the thermal aspects, then one very important consideration for choosing a material is the thermal conductivity, because if you think of the railway line example that I have given in the last class, the railway lines if they have a high degree of thermal expansion, then the lines will have a high degree of thermal stress, because you have to contain that expansion, and that thermal stress will create failure in the lines. So, hence you have to choose a material which should have a reasonably lower degree of thermal conductivity. Again, for other applications you may need actually high degree of thermal conductivity. Okay. So, wherever you need actually the temperature, say for example heat exchangers. Okay. So, you need a high degree of thermal conductivity, so that the heat that is coming from a system can be very quickly dissipated. The other important point is the specific heat. Now, specific heat is what? That is the heat capacity per unit mass of a system. So, the specific heat plays an important role in terms of denoting that how much of heat can be absorbed by a system. Okay, for the entire environmental issue, for example, the water to land ratio is actually controlled by the specific heat, because it is the water which has the high capacity of specific heat, and hence it can absorb more heat in comparison to the land. So, the water heated up much slower at a much slower rate in comparison to the land, and as a result the circulation, the environmental circulations occur. So, specific heat play a very important role in terms of various types of systems at different scales. Then of course, you have the thermal expansion coefficient there, and the thermal expansion coefficient, just like the thermal conductivity, is very very important for this type of applications where the expansion coefficient is to be either controlled within a certain degree. For example, I gave you the railway line example, there again the thermal expansion coefficient is important. You again have to choose a material which must have a low thermal expansion coefficient, so that it does not expand much. Okay. So, and there are cases where higher degree of thermal expansion coefficient is used, particularly when you make switches for make or break type of a thing. So, there the temperature is used in such a manner that a large expansion is possible and a switching of a system is possible through that. So, this is the thermal related parameters. Then of course, there are some general physical parameters, just a few of them if you look at it are like density, resistivity, these are very general physical parameters, but we do look for it in terms of choosing a material whenever they are very important. For example, a low weight, that means a low density is always important for aerospace type of applications. Electrical and magnetic properties, these are becoming very important even for mechanical systems today. So, there are things like resistivity, like dielectric constants, like magnetic permeability. These are the parameters which are very important whenever you are thinking of an electromechanical system. Okay. Just for example, you think of a system which contains some amount of magnetic systems inside it. Okay. So, if you think of any such system, okay, which has a magnet inside this whole thing. Okay. So, for example, a motor. Okay. Now, the magnetic field permeability is very important because the higher the permeability, the better will be the induction by the motor, the more magnetic field it will be able to generate. On the other hand, there are applications where you will need that if there are two such magnets for two different reasons, the magnets should not interfere with each other. So, that means you should need a material in between which will not allow the magnetic field to pass from one part to the other. So, here we talk about actually EMI shielding kind of things. So, that is how the electrical and magnetic fields become important for various systems. Next is the environmental interactions. So, here in the environmental interactions this is specifically important for mechanical systems. For example, the oxidation, because all mechanical systems when they are subjected or exposed to environment, then there is always oxidation that happens in the system. So, you need to give a good protection from oxidation, and sometimes there are other corrosive gases. So, you need to give even protections from corrosions for them. So, oxidations and corrosions are very important factor in terms of those mechanical systems which are generally subjected to the possibilities of environmental vagaries or the possibilities of harmful chemicals conducting, say for example, gas pipelines. Okay. So, there the chances of corrosion is very high. So, you need to choose a material which will not be getting corroded so fast, in that way reduce the life of the pipeline. So, thus oxidation, corrosion are important, and wear, of course, it is important because there are many mechanical systems in which the relative velocity between the two components always occur. If you think of a mechanism, there is always the relative velocity between the links of a mechanism. So, in such cases there will be a wear that will be constantly happening in the system, and this wear is to be controlled in terms of controlling the life of the system. So, environmental interaction effects are thus very important considerations, particularly for mechanical systems. And next is from the production perspective, we also look for properties which are important from the production point of view. For example, which material is good in terms of the manufacturing point of view. I can give you an example that if you consider between say iron, okay, and something like a titanium, okay, which is used as a space grade application because of its high temperature, very good high temperature properties. Now, in terms of ease of manufacturing, however, iron you can shape it much better. Okay, you can actually work on iron in order to give various complex shapes, etc., in a much easier manner in comparison to titanium. So, from the ease of manufacturing point of view, a material, even though may have other good mechanical properties, may not be suitable from the ease of manufacturing point of view. Similarly, there are certain other subclasses of productions like joining, like finishings. So, all these things together are to be taken care of in the production phase, and hence it affects when we are choosing a particular material. Now, last but not the least, I told you about 7 important properties, but there is the 8th one that is of course generally beyond the scope of our dealing, but it is actually the aesthetic properties, which in today's context is to be always kept in mind, because after all, if you cannot give, particularly for the consumer goods, if you cannot give an attractive look to a system, the product will not sell. So, hence properties like color, properties like texture, the feel of it, etc., this becomes important. So, certain materials, I told you that metals give a typical metallic lustre. Also, metals give a typical metallic ringing sound. So, from various aesthetic point of views, metals have a different charm in comparison to the other things like ceramics or plastics. Okay, if you consider, say for example, from the thermal conductivity point of view, how that can get coupled with aesthetic. Any metallic product, as you know, they are highly thermally conductive. So, what happens is that if you in an area where there is a very the climatic condition is very severe, like say severe cold condition, under such places a metallic system, the moment you touch it, you will never feel the warmth of the system. So, if you develop a metallic casing, let us say of a cell phone, will not go very well. On the other hand, if you make it out of polymers, they being thermally insulating type, they will not lose their temperature, and hence they will give a much better feel or comfort. So, thus aesthetic properties often becomes important in terms of choosing a particular material, particularly when we talk about the consumer type of products. Okay. So, that is about the overall material properties. Now, we let us look into specifically the mechanical properties of the material. There are actually a very large list of mechanical properties, but I have chosen a few of the very important ones which you will need for example, for the day to day mechanical design, the strength of the material, the stiffness, which is actually governed by the modulus of elasticity, then the plasticity from the forming point of view, ductility and malleability. This is one common point that you often come across, that ductility and malleability are not the same, okay? Because both of them of course refers to that how you are deforming a material, mainly the plastic deformation, but while ductility refers to the deformation under tensile condition, the malleability generally refers to deformation under compressive conditions. So, ductility, for example, refers to if I can actually reduce the thickness of a wire as I am applying a kind of a large tensile load. Okay, can I draw a very thin wire from a cylinder? So, if the material has a good ductility, you can draw a very thin wire out of it. So, that is in the context of tensile loading. On the other hand, malleability is a property which talks about that suppose if I compress something like clay, you can actually mold it, you can give different shapes to it. So, malleability refers to the compressive loading, susceptibility to compressive loading. That is why the two are different. Then of course, we talk about strength, specifically the tensile strength, because that becomes important, and the toughness and the hardness of a material. So, these are some of the mechanical properties which we will be discussing in much more details. Okay. So, before I talk about the strength, I should talk about the concept of stress and strain, which is very, very basic and important for any mechanical component. Now, the way we will define stress here, it is the very elementary definition of it is that it actually depicts the internal resistance per unit area in an average sense that acts on a material when you are trying to deform a material. So, for example, if you use a tensile testing machine, then you will be taking a sample where you are actually going to apply the force and deform the material, like you can deform it either in a tensile force system, in this manner, where you are actually pulling it apart, or you are compressing it. In both the cases, you have an idea of how much of force you are applying, and you know that what is the area of cross section of the system, okay? The initial area of cross section of the system. So, in an average sense, the force per unit area will give you the stress. Okay? Now, the stress is generally actually the SI standard unit is Newton per square meter for stress, okay? And that is also called Pascal, named after the famous mathematician who has a very important contribution in terms of hydrostatic stress. Now, even though Pascal is the unit, but generally the type of systems that we come across will have something like kilopascal or megapascal or gigapascal kind of range of stress. Okay? So, in fact, the way stress is related to strain is also called the modulus of elasticity. So, if you look at the modulus of elasticity, which has the same unit in terms of Pascal, then just to give you a feel of it, that something like a chocolate will have a modulus of elasticity which is between 100 Pascal to a kilopascal range. If you think of something like rubber, it will have modulus of elasticity between kilopascal to megapascal range. If you think of steel, you get modulus of elasticity which is between megapascal to gigapascal, definitely in the gigapascal range, 200 gigapascal or so. So, that is a kind of an idea which tells us that what is this kilopascal, megapascal or gigapascal. So, next time you deform a chocolate, you may know that you are actually doing it at something like 100 Pascal level. If you are doing it with a rubber, it is at the megapascal level, and if you are doing it with any metal, it is definitely beyond several gigapascal. Okay? So, that is where you cannot actually do it manually, you need a machine to apply the force. I will talk about that machine which is used in that context. So, thus you can understand that what is stress, okay, which is the internal resistive force, as I told you, averaged out for an area over which this force is working on, and the unit of it, that is the Pascal, that we know. Now, what is actually the strain of the material? The strain is defined in terms of the change in length per original length of the material. Now, here if we think that the area of cross section is not changing or the change is small in a certain range, then the strain is actually the engineering strain or a conventional strain or a normal strain, which is actually the change in length over the original length of the material. So, that is what is your strain, and the strain is measured because generally this strain is very, very small. So, the strain is measured in terms of 10 to the power minus 6 or micron strain, using which the strain is measured in a material. So, thus these are the two very basic important points about stress and strain that you need to know. Now, stress need not be always tensile in nature or need not be always compressive in nature. There can be stresses which can be shearing in nature. Okay? And say for example, in this particular case, if you look at it, that there is a block of mass here over which we are applying a shearing force. Okay? So, that is why the block is actually deforming from its initial position to this kind of a new deformed shape from its initial shape. Okay? So, that is the deformed shape of the block. So, this kind of deformation, where it is neither, you cannot call it expansion or contraction, but it is moving, relative movement of one surface with respect to the other, that is what is the shear. So, that type of resistance is measured in terms of shear stress, where it is the shearing force over the area over which the shearing is happening. And the shear strain in this case is actually the lateral displacement, that is delta, that is the lateral displacement, and over the distance between the two faces. Okay, that is what is L. Okay, so that is the distance between the two faces. So, that is also you may actually express it as tan theta. Now, whenever this is very, very small, then you know that tan theta becomes almost equal to theta, and hence for small strain condition, shear is often expressed in terms of the angle theta. Okay. Now, there are many day-to-day examples. See, I in the last class told you about the doubly balanced cantilever beam, that is used, or the doubly balanced cantilever system that is used for the bridge, the Howrah bridge, for example. Okay, so there you will, if you look at it, such kind of bridge construction, you will see a beautiful manifestation of single shear and double shear. Okay. So, for example, if you have two plates which are just lapped with each other, and then you are using one single bolt to actually lock it, and then you are applying the shearing force, okay, on the plate system, then what you have is a single shear, because the bolt has to fail across this area of cross section. So, that is what is the shear stress that is happening. Okay. So, that shear stress is of a much higher level, corresponding to the force you are getting only this much of area. Okay. But if you have a system with the same bolt, and if you have a system where you have two such elements in one side and the other one is in the other side, so you are joining in that manner, and this is how the bolt is, then there are two surface areas which comes into picture. So, that actually the force becomes half in that sense. So, that means the shear stress level comes down. So, thus you can actually make many such changes intelligently in a system, so that the shearing stress actually comes down, and thus it gives you a stronger system with a better life. So, that is what is the shear stress. Now, there is also another manifestation of shear stress, we call it pure shear. This happens, of course, in terms of torsion, okay, which is a variation of a pure shear. Now, in the torsion, what happens is that a structural member is twisted in a manner that the torsional force, for example, in this case you are actually twisting this member, you are actually twisting this member, okay, in a manner that it produces a kind of a rotational deformation or a rotational motion of the top surface with respect to the bottom surface, where it is hold, let us say it is fixed at this point. Okay. So, this kind of a thing, where there is again a relative movement between the two surface, they are standard of any torsional situation, and they are generally governed by this kind of a standard relationship for very small twisting angle. Okay. So, when the twisting angle is not very high, it is torque over the polar moment of inertia equals to the shear stress tau over r, and that equals to the shear modulus of elasticity G over phi. Phi is that angle of twist, phi is this angle over the length L of the sample. Okay. So, one can actually find out that what is the shear stress corresponding to the pure shear condition, provided you know that what is the modulus of elasticity, you know what is the twisting angle, you know what is the radius of the shaft or the length of the specimen. So, that is a special case or manifestation of shear, which is called the torsion. Now, where it is important, there are these machine axles, drive shafts, aircraft wings, for example, or drills, where this type of a system, the torsional system, are very heavily used. Now, what are the other common states of stress? Of course, you in a day to day experience you must have seen this kind of simple tensions in something like a copy call, or something like pulley based systems, okay, or something like a column. You will see a simple compression case, but there are other cases, for example, a balloon, okay, or any such hydrostatic bodies where you get a biaxial state of stress, okay, expansion and contractions, or a hydrostatic pressure you can see, or there are cases where you will be able to see the pure shear. So, these are all certain cases of stress in our day to day experience. So, these are certain common states of stress, and this is where we will actually finish today's lecture, and what we will be discussing next, actually we will talk about this concept of stress and strain and the constitutive relationship in much more depth in the next lecture. Thank you.